Welcome to the Nocturnal Astronomer. This is a space built for quiet evenings, for the moments when the day has finally slowed down and you find yourself ready to rest. Whether you are drifting off to sleep, relaxing after a long week, or simply looking for something calm and thoughtful to fill the background of your evening, you have found the right place. My name is Atlas Reed, and I will be your guide through the universe tonight. Together, we explore the deep mysteries of space, told slowly and gently, without hurry and without clutter. The cosmos is vast and ancient and endlessly fascinating, and there is no better companion for a quiet night. Tonight, we are going on a journey, not to a distant galaxy or a far-off star, though those will certainly come up. Tonight, the journey is much closer to home. Tonight, we are going to follow the atoms inside your very body, tracing where they came from, what they have witnessed, and what astonishing paths they took to arrive here, right now, as part of you. Let's dive in. Part 1. You are made of stars. Every atom in your body has a story. Not a short story either, but one that stretches back nearly 14 billion years, through fire and silence and unimaginable cold, through the hearts of dying stars and the wreckage of ancient explosions. Your atoms are not new. They are extraordinarily old. The iron in your blood was forged inside a massive star that died before our sun was born. The calcium in your bones was built in the churning core of a stellar furnace that no longer exists. The oxygen you breathe in and out every few seconds was scattered into space by forces so powerful they briefly outshone entire galaxies. This is not a metaphor. This is documented, observable, measurable fact. The elements that make up your body were created through nuclear processes that scientists have studied for decades. And the story of those processes is one of the most breathtaking discoveries in the history of science. The phrase you may have heard, that we are made of stardust, is often repeated so casually that it can begin to feel like something poetic rather than something literal. But it is quite literal. The atoms in your hand right now were once inside a star. That is simply true. To understand the journey those atoms have taken, we need to begin at the very beginning. We need to go back to a time before stars existed at all, to the first few minutes of the universe, when the only things in existence were the simplest possible building blocks and an almost unimaginable amount of energy. The universe began in a state of extraordinary heat and density. Everything that would eventually become galaxies, stars, planets, oceans, forests, and people was compressed into a space far smaller than any star, radiating energy in all directions, expanding outward at a rate that strains every human intuition about what expansion even means. In the first fraction of a second, the universe was a soup of particles, so energetic they could not yet combine into atoms. Protons and neutrons and electrons and photons all collided with each other constantly in a state of dense, brilliant chaos that would be completely unrecognizable to anyone alive today. Then, as the universe expanded, it began to cool. Cooling is a word we use loosely here. The temperatures were still staggeringly high by any human standard, but relative to what they had been moments before, the universe was calming down, and that cooling made all the difference. Within the first 3 minutes, something remarkable happened. Protons and neutrons began combining with each other. Simple atomic nuclei formed for the first time. Mostly hydrogen, the simplest element, just a single proton. And some helium formed when 2 protons and 2 neutrons locked together. A small amount of lithium also appeared. And then the window closed. The universe cooled past the point where further nuclear fusion could take place on its own. For hundreds of thousands of years after that, the universe was a vast, dark, mostly featureless expanse of hydrogen and helium gas, drifting and cooling in the dark. No stars, no planets, no light sources at all, just atoms slowly spreading outward into a growing void. Part 2. The first stars are born. For a very long time, the universe was quiet. There were no stars, no light, no fire anywhere in the cosmos. Astronomers call this period the Cosmic Dark Ages, and it lasted for tens of millions of years. The universe was not empty, but it was dark, and the atoms drifting through it had nowhere to go, except where gravity gently pulled them. Gravity, while subtle over short distances, becomes enormously powerful when given enough material to work with. Tiny fluctuations in density from the earliest moments of the universe caused some regions of space to accumulate gas slightly faster than others. Those regions grew denser over time. Denser regions pulled in more gas, which made them denser still. Think of it like a gentle slope in a landscape, almost too slight to notice. But a drop of water placed on that slope will roll, and as it rolls, it gathers more water, and the stream grows wider, and eventually something significant is moving. Gravity works something like that, only across distances that make the mind go quiet. As clouds of hydrogen and helium collapsed inward under their own gravity, they began to heat up. Compressing a gas releases energy, and the energy had nowhere to escape, so the temperatures inside these clouds climbed higher and higher. The centers of the largest clouds became extraordinarily hot, far hotter than anything humans have ever directly created. When the temperature at the core of a collapsing cloud reached about 10 million degrees, something new began. Hydrogen nuclei, moving at tremendous speed due to the heat, started colliding with enough force to fuse together. Nuclear fusion had begun. The first stars were igniting, and the cosmic dark ages were ending. These first stars were unlike the stars we see in the sky today. They were enormous, sometimes hundreds of times more massive than our sun. They burned through their hydrogen fuel at a furious pace, living fast and brilliantly, and dying young. A star like our sun lives for roughly 10 billion years. These early giants burned out in just a few million. Inside those massive early stars, the fusion process did not stop at hydrogen. Once the hydrogen in the core was spent, the star began fusing helium. When the helium was gone, it fused carbon, then oxygen, then neon, then silicon. Each stage burned hotter and faster than the last, like a fire that keeps finding new fuel just as the old fuel runs dry. At the end of this chain, silicon fusion produced iron. Iron is a critical element in this story because it sits at the peak of what is called the nuclear binding energy curve. It is, in a sense, the most stable nucleus that fusion can produce. Fusing iron does not release energy, it requires energy, and that changes everything. When an iron core builds up at the center of a massive star, fusion can no longer generate the outward pressure needed to balance gravity's inward pull. The core becomes unsupported. In a fraction of a second, it collapses. What happens next is one of the most violent events in the known universe. The collapse of the iron core sends a shockwave outward through the rest of the star at enormous speed. The outer layers, which had been held up for millions of years by the energy of fusion, are blasted outward into space. The star explodes as a supernova, briefly shining with the brightness of an entire galaxy of stars combined. Part 3. Elements scattered into space. In the final moments of a massive star's life, and in the ferocious environment of the supernova explosion itself, elements heavier than iron are created. Gold, silver, platinum, uranium, and many others require conditions so extreme that only the death of a massive star can produce them. Every gold ring ever made contains atoms born in a supernova. The explosion scatters all of these elements outward in an expanding shell of gas and debris. This shell moves into the surrounding space at thousands of kilometers per second, sweeping up material along the way, and gradually slowing as it encounters the thin gas of the wider galaxy. Astronomers can observe these expanding shells today. They are called supernova remnants. One of the most visually stunning examples is the Crab Nebula, the remains of a star that was observed by astronomers around the world almost 1,000 years ago. Today, it spans roughly 11 light years across and is still expanding. Inside, it is a rapidly spinning neutron star, the crushed remnant of the original stellar core. The elements released in these explosions mix into the surrounding gas clouds of the galaxy. Over time, those enriched clouds become the raw material for new generations of stars and new planetary systems, and eventually new worlds. Each generation of stars adds more heavy elements to the galactic mix. The universe grows gradually richer in complexity. Our own solar system formed from a cloud that had already been enriched by earlier generations of stars. The iron in your blood, the calcium in your teeth, the oxygen in your lungs. These elements were scattered into our region of the galaxy by stars that lived and died long before the sun was born. There is something quietly moving about that. The atoms inside you carry a kind of deep history, a lineage that runs back through stellar deaths and cosmic explosions and the long, cold drift of interstellar space. Your body is, in a meaningful sense, built from the ashes of ancient fires you will never see. Some of the atoms in your body may have been through more than one cycle of stellar birth and death. A star forms, burns, explodes. Its material drifts in space. Part of it gets swept into a new star-forming cloud, condenses into a new star, burns again, and explodes again. The atoms ride the cycle, patient and unchanged. Between stellar cycles, atoms spend enormous stretches of time simply drifting through interstellar space. Space is not truly empty. It contains gas at extremely low densities, thin clouds of hydrogen and helium and heavier elements, threaded through by magnetic fields and bathed in the faint light of distant stars. Your atoms have drifted through all of that. The journey of an atom through interstellar space is immeasurably slow by human standards. Atoms can spend hundreds of millions of years in the thin gas between star systems, slowly moving under the subtle influence of gravity, radiation pressure, and the gentle stirring of galactic dynamics. Time at that scale is hard to hold in mind. But atoms are patient. They do not age. They do not decay in any meaningful sense under ordinary conditions. A carbon atom forged in a stellar core 4 billion years ago is chemically and physically identical to one forged yesterday. The universe has a long memory, and your atoms are part of it. Part 4. A new solar system forms. About 4.5 billion years ago, in one of the outer spiral arms of the Milky Way, a large cloud of gas and dust began to collapse. What triggered the collapse is not entirely certain. It may have been a nearby supernova sending a pressure wave through the cloud, or simply the slow accumulation of enough mass to tip the balance. Whatever the trigger, the cloud began to draw inward. As it collapsed, it began to spin. This is a consequence of a physical law called the conservation of angular momentum. A large, slowly rotating cloud, as it shrinks, rotates faster and faster, much like a figure skater pulling in their arms during a spin. The spinning caused the cloud to flatten into a disk. Material along the plane of rotation could not fall straight inward because it was moving sideways too quickly. Instead, it settled into a broad, flat structure, with the densest and hottest material concentrated at the center. That center would become our sun. Within a few 100,000 years, the central mass had grown large and hot enough to ignite nuclear fusion. Our sun turned on. For the first time, light radiated outward from this new star, and the material in the surrounding disk began to feel the warmth and pressure of solar radiation pushing outward against it. In the disk around the young sun, material was colliding and clumping together. Dust grains stuck to each other, forming pebbles. Pebbles collided and merged into larger rocks. Rocks built into boulders, and boulders into bodies large enough for their own gravity to pull in more material. This process, called accretion, was underway across the whole disk. In the inner regions of the disk, close to the sun, only the most heat-resistant materials could survive. Rocky and metallic compounds stayed solid, while lighter, more volatile materials were driven further out by heat and solar wind. This sorting process is why the inner planets are rocky and the outer planets are made largely of gas and ice. The Earth took shape over tens of millions of years. It was a very different world then. The surface was hot and frequently struck by large bodies that were still being cleared from the early solar system. Impacts were common and sometimes enormous. One such impact early in Earth's history likely led to the formation of our moon. A body roughly the size of Mars is thought to have collided with the young Earth at an angle, ejecting a vast quantity of material into orbit around our planet. That material gradually coalesced into the moon. The collision also tilted Earth's axis, which is why we have seasons. A single ancient impact still shapes your year, even now. Gradually, Earth cooled. A solid crust formed over a still molten interior. Volcanic activity was intense, and the young atmosphere was nothing like the one we breathe today. It was thick with carbon dioxide and water vapor and various gases, and it lacked the oxygen that most life on Earth now depends on. That would come later. The atoms that would eventually become part of you were present in this young world, scattered through the rocks and gases and oceans of the early Earth. They had no particular destination in mind. Atoms do not have destinations, but the processes of geology and chemistry, and eventually biology, would begin to sort and gather them step by slow step. Part 5. The Chemistry of Early Earth. The early Earth was a world in constant motion. Tectonic plates were shifting, volcanoes were erupting frequently, pouring gases and lava across the surface. The oceans were forming as water vapor condensed and fell as rain over thousands of years. And something was also arriving from space. Comets and asteroids were striking the young Earth in large numbers during a period astronomers call the Late Heavy Bombardment. These impactors brought with them water ice, organic molecules, and carbon compounds. Some researchers believe that a significant portion of Earth's water and much of the raw chemical material for life arrived this way, delivered from the outer solar system. Organic molecules are not inherently biological. The word organic in chemistry simply refers to carbon-based molecules. Carbon is a remarkable element because of its ability to form long chains and complex structures with other atoms, particularly hydrogen, oxygen, and nitrogen. These properties make carbon the backbone of all known life on Earth. In the oceans of early Earth, and particularly around hydrothermal vents on the ocean floor, chemical reactions were taking place constantly. Heat and chemical gradients drove molecules to combine in new ways. Amino acids, the building blocks of proteins, can form under these conditions. Scientists have created amino acids in laboratory simulations of early Earth conditions. The question of how life actually began, meaning how a collection of chemical reactions crossed the threshold into something that could replicate itself, is still one of the deepest open questions in science. We do not have a fully agreed upon answer, but we know that the chemical preconditions were present, and we know that life did appear, because here we are. The earliest evidence of life on Earth comes from microbial fossils and chemical signatures preserved in ancient rocks. The oldest of these signs suggest life may have been present on Earth as long as 3.5 billion years ago, and possibly earlier. These were simple, single-celled organisms, but they were alive, and they were changing the planet. Early microbial life did not require oxygen. The atmosphere at that time had very little of it. Instead, these early organisms used other chemical processes to extract energy from their environment. But one group in particular would eventually change the entire character of Earth's atmosphere in a way that reshaped the story of life entirely. Cyanobacteria, a type of photosynthetic microbe, began using sunlight and water to produce energy, releasing oxygen as a byproduct. as their populations grew over hundreds of millions of years, they pumped increasing amounts of oxygen into the atmosphere. This was a world-altering event, so significant that it is sometimes called the Great Oxidation Event. For organisms that had evolved in an oxygen-poor world, this new oxygen was actually toxic. Many species went extinct as oxygen levels rose. But for other organisms, oxygen represented a tremendous opportunity. It allows for far more efficient energy extraction from food. Life that could use oxygen could potentially be far more complex and active than anything before it. The atoms that are now in your body were part of this ancient microbial world. The carbon in your cells may have cycled through dozens of different organisms across billions of years. The oxygen in your bloodstream is part of a cycle that tiny photosynthetic creatures began building hundreds of millions of years before the first fish ever swam. Part 6. Life grows more complex. For most of Earth's history, life was microbial. Single-celled organisms dominated the planet for billions of years. This is easy to overlook when we think about the history of life, because we tend to focus on the more dramatic chapters involving animals and plants and the eventual appearance of humans. But the microbial age was enormously long and consequential. A critical step in the evolution of complex life was the development of the eukaryotic cell. Unlike the simpler cells of bacteria and their relatives, eukaryotic cells have a distinct nucleus that holds the genetic material, and they contain specialized structures called organelles that carry out specific functions. Most of the life you can see with the naked eye is made of eukaryotic cells. One of the most fascinating ideas in biology is that some of these organelles were once independent organisms. The mitochondria in your cells, the structures that convert food into usable energy, are thought to be descended from ancient bacteria that were absorbed by a larger cell long ago and eventually became permanent, integrated partners. Your cells are, in a sense, ancient communities. The first multicellular organisms appeared roughly 1 billion years ago, though the exact timing and the earliest forms are still studied and debated. Cells began cooperating, taking on different roles, forming structures together. The advantage of cooperation was significant. Larger, more specialized organisms could do things that single cells never could. The Cambrian period, which began roughly 540 million years ago, saw an extraordinary diversification of animal life. Within a geologically short period, the fossil record shows the appearance of most of the major animal body plans we recognize today. Eyes, limbs, shells, jaws, nervous systems, all of these appeared in a burst of biological innovation. Life moved from the oceans onto land roughly 450 million years ago. Early plants colonized the shores first, followed by arthropods, and eventually by vertebrates that hauled themselves out of shallow water on the ancestors of what would become limbs. The transition was not sudden, but spread over millions of years of gradual adaptation. The atoms in your body have been through much of this story. Carbon atoms in your body may have once been part of an ancient tree, dissolved into soil, washed into an ocean, incorporated into a shell, buried in sediment, compressed into rock, and then released by geological processes millions of years later. The paths are tangled and long. Throughout all of this time, atoms themselves did not change. They participated in reactions, bonded and separated, moved from one molecule to another, from one organism to another, from sea to sky to soil and back again. But the atoms themselves remained. An atom of calcium that was once part of a dinosaur bone is chemically the same atom today. Mass extinctions punctuated the history of life and reshuffled which atoms ended up in which organisms. The mass extinction at the end of the Permian period, roughly 252 million years ago, is estimated to have wiped out more than 90% of all species. The atoms released from those extinct creatures eventually entered new life forms. The extinction that ended the age of the non-avian dinosaurs, roughly 66 million years ago, opened ecological niches that mammals began to fill. The small, warm-blooded, night-adapted creatures that survived that catastrophe would eventually give rise to all the mammals alive today, including the primates, including us. Your atoms have been on a very long detour to reach you. Part 7. Primates, and then us. Primates appeared roughly 60 million years ago. The earliest were small, tree-dwelling creatures, probably resembling the small lemurs and tarsiers alive today. Over millions of years, primate lineages diversified, and some developed characteristics that would eventually become defining features of the human line. Larger brains, forward-facing eyes, and flexible hands capable of fine manipulation. About 6 or 7 million years ago, in Africa, the lineage leading to humans began to diverge from the lineage leading to our closest living relatives, the chimpanzees and bonobos. This does not mean we descended from chimpanzees. It means we share a common ancestor, a population of primates that existed before either lineage had taken its current form. The human lineage passed through many stages. The genus Australopithecus walked upright on 2 legs, but had a brain not much larger than a chimpanzee's. Later came Homo habilis, associated with early stone tool use. Then Homo erectus, who spread out of Africa and colonized parts of Asia and Europe over a period of nearly 2 million years. Our own species, Homo sapiens, appeared in Africa roughly 300,000 years ago. For most of that time, we were hunter-gatherers, moving across landscapes, adapting to different climates, and gradually accumulating knowledge, culture, and technology. we were a successful species in many environments, though not yet dominant in the way we would later become. Modern humans reached Europe and Asia tens of thousands of years ago, where they encountered and interbred with other archaic human populations, including the Neanderthals and a group known from genetic evidence called the Denisovans. Most people alive today carry small percentages of DNA from these other human lineages, a quiet molecular reminder of ancient encounters. The emergence of symbolic thinking, language, art, and complex social structures in our ancestors marks one of the most significant transitions in the long history of life on Earth. No other animal builds cities, writes music, or sends spacecraft to study distant planets. The atoms inside you are the first atoms in the known history of the universe to participate in all of that. The atoms that make up a human body did not evolve. Bodies evolved, and the biological processes that govern how atoms are assembled into bodies evolved. But the atoms themselves arrived in the universe long before evolution existed, and they will persist long after any particular species has run its course. You are a temporary arrangement of very ancient material. Agriculture began roughly 10,000 years ago, and with it came a shift in how atoms moved through human populations. Instead of hunting and gathering atoms from a broad landscape, humans began cycling atoms through cultivated fields and domesticated animals in dense, concentrated communities. Cities are, among other things, extraordinary gatherings of atomic material from many distant sources. Every meal you have ever eaten has introduced new atoms into your body and sent old ones on their way. The food on your table has a geographic history. Water from rivers, minerals from soils, energy from sunlight converted by plants. The atoms in your dinner tonight may have been growing in a field very far away just a few weeks ago. And before the field, those atoms had other histories entirely. The carbon in a tomato was recently atmospheric carbon dioxide, absorbed by the plant through its leaves. Before that, it may have been exhaled by an animal, or released by decomposing soil, or emitted by a volcanic vent. Carbon cycles through the biosphere constantly, and through you along with it. Part 8. The atoms inside you now. The human body is composed of roughly 7,000 quadrillion atoms. That number is so large it effectively defies any intuitive grasp. It is more atoms than there are stars in the observable universe, by many orders of magnitude. You are, in terms of sheer atomic count, an almost incomprehensibly large structure. About 65% of your body by mass is oxygen. About 18% is carbon. About 10% is hydrogen. Nitrogen, calcium, and phosphorus make up most of the remainder, with dozens of other elements present in smaller but often critical amounts. The iron in your blood, though tiny in proportion, is essential to every breath you take. Interestingly, your body is not the same collection of atoms from one year to the next. Atoms cycle through your tissues at different rates, but the turnover is constant. The cells lining your stomach are replaced roughly every few days. The carbon atoms in your bones are replaced over a period of years. Your body is less a fixed structure and more a pattern that matter flows through. This means that the majority of the atoms in your body right now were not there 10 years ago. Some have been in you for a while. Others arrived recently in your food and water and the air you breathe. You are, in a very real sense, a temporary gathering place for atoms that have been in many other places and will go to many more. The water in your body is perhaps the most widely traveled component. Water molecules cycle through the global hydrosphere constantly. The water you drank today has evaporated from oceans, fallen as rain, seeped through soil, flowed through rivers, and possibly passed through the bodies of countless other organisms over thousands of years before arriving in your glass. There is a famous thought experiment that calculates the probability that any glass of water contains at least one molecule that was once inside a famous historical figure. Given the enormous number of molecules in a glass of water and the degree to which the global water supply has been mixed and recycled over millennia, the answer is almost certainly yes. The nitrogen in your body follows a similarly intricate path. Nitrogen is essential for building amino acids and therefore proteins. Your body cannot pull nitrogen directly from the air, even though the atmosphere is roughly 78% nitrogen gas. Instead, you absorb nitrogen through food, which absorbs it from soil, which gets it from bacteria that can fix atmospheric nitrogen into usable forms. The phosphorus in your bones was once part of ancient rocks, dissolved by weathering over geological time, washed into oceans, concentrated in sediments, incorporated into marine organisms, eventually compressed back into rock, and then released again by erosion. Phosphorus cycles are slower than carbon or nitrogen cycles, taking millions of years to complete a full turn. The calcium in your skeleton was forged in stellar interiors, scattered by stellar explosions, incorporated into the young Earth, cycled through oceans and rocks and organisms across billions of years, and now holds your skeleton together. When you stand up, ancient starfire is keeping you upright. Every element in your body has a story like this. Every atom is a traveler. Your body is not just a biological system. It is an intersection point for billions of years of cosmic and geological and biological history, momentarily gathered into this particular form, this particular arrangement that thinks and feels and breathes, and perhaps tonight is drifting gently towards sleep. Part 9. Where your atoms will go. Atoms do not die. This is a fundamental truth of physics. The atoms in your body will continue long after you do, moving on into new forms, new systems, new organisms. The end of a human life is, from the perspective of atoms, simply a change in address. They will be going somewhere. They always are. When an organism dies and decomposes, its atoms are released into the surrounding environment. Microbes break down organic molecules, releasing carbon back into the atmosphere as carbon dioxide and returning nitrogen and other nutrients to the soil. The atoms spread outward from the body and become available to other organisms nearby. A tree growing nearby may absorb carbon from the air that was recently part of a living creature. An insect may eat a leaf from that tree and absorb atoms that were recently soil bacteria. A bird may eat the insect. A fox may eat the bird. Atoms move through food webs constantly, passing from one life form to the next without pause or ceremony. Some atoms may become trapped in sediment and spend millions of years compressed into stone before being released by geological processes. The carbon locked in coal and oil was once living material, ancient forests and marine organisms from hundreds of millions of years ago, held in geological storage until extracted and burned by human civilization. Other atoms may be carried by wind and rain to distant places. A molecule of water that evaporates from the ocean may travel thousands of kilometers before falling as snow on a mountain range. The atoms in that snowflake will eventually melt, flow downhill, join a river, reach the sea, and begin the cycle again. On geological timescales, atoms that are locked in rock are eventually returned to the surface through the slow churning of tectonic plates. Material that sinks into the mantle is eventually released again through volcanic activity. The whole solid Earth is slowly cycling, sorting, and redistributing its atomic inventory over hundreds of millions of years. On even longer timescales, atoms in the outer atmosphere of Earth can escape into space. Hydrogen is light enough that some molecules at the top of the atmosphere achieve sufficient velocity to overcome Earth's gravity and drift away into the solar system. Very slowly, over billions of years, the Earth does lose some of its lightest material to space. On the longest timescales of all, the Sun will eventually evolve into a red giant star, expanding outward to engulf the inner planets. The Earth's surface will be consumed, and the atoms that were once oceans and mountains and living creatures will be scattered into the solar system. They will eventually be carried outward by stellar winds as the Sun sheds its outer layers. Those atoms will drift again through interstellar space, perhaps for billions of years, perhaps finding their way into a new star-forming cloud, perhaps eventually becoming part of another solar system, another planet, another ocean, another form of life in a future we cannot imagine. The cycle that began at the dawn of the universe will continue. From a certain perspective, there is something deeply comforting about this. Nothing that makes up who you are is truly lost. The atoms are permanent travelers, and their journey does not end. The particular arrangement called you is temporary, as all particular arrangements are. But the material itself goes on, as it always has, into whatever comes next. Part 10. The Meaning of the Journey. We have traced a path that begins at the birth of the universe and arrives after 14 billion years and an almost incomprehensible series of events at the atoms inside a person, sitting quietly, perhaps with the lights turned down, listening to the sound of someone talking about the night sky. That is an extraordinary journey by any measure. The physicist Carl Sagan wrote that we are a way for the cosmos to know itself. That thought has stayed with many people because it captures something that feels true but is hard to put precisely. The universe spent billions of years building the conditions for consciousness. And consciousness, once it arrived, began looking back at the universe and asking where it came from. The fact that we can tell this story at all is remarkable. The atoms in your brain, assembled through billions of years of cosmic and biological history, are capable of forming models of that history, of reasoning about processes that happened before our planet existed, of calculating what happens inside a stellar core using only mathematics and observation. Astronomy has a way of putting scale into relief. The universe is old and vast in ways that are genuinely difficult to hold in the mind. But rather than making human life seem small, many people find that understanding the scale of things has the opposite effect. The improbability of your existence, given all that had to happen to produce you, is staggering. Consider what was required. The universe had to begin in precisely the right conditions. The laws of physics had to permit the formation of stable atoms. Stars had to form and live and die in just the right ways to produce the elements your body needs. A solar system had to form around a stable star. A planet had to emerge at the right distance with the right chemistry. Life had to emerge on that planet, survive mass extinctions, evolve toward complexity, develop intelligence and culture and language. A very particular chain of ancestors had to meet and reproduce all the way back through human history, and before it, through millions of years of primate evolution, through the first mammals, back through the oceans and the first cells. Every link in that chain, going back billions of years, had to survive. Any break anywhere along the way, and the particular arrangement of atoms that is you would not exist. The atoms would exist, scattered through other forms, but you specifically required every single prior event to unfold in precisely the way it did. That is humbling in the most peaceful possible sense. There is a quality to this knowledge that is well suited to the end of a day. When the noise of the world quiets down and there is nothing left to do, it can be grounding to remember that you are not separate from the universe. You are made of it. The atoms in your body are as old as creation. They have been in stars. They have drifted through galactic space. You carry that history inside you right now, in every breath and every heartbeat. The oxygen filling your lungs was produced by ancient stars and cycled through the Earth's atmosphere for billions of years. The carbon in your cells was forged in stellar cores. The iron carrying oxygen through your blood is the same iron that made stars collapse and explode across the sky of a universe that had not yet imagined planets. And for now, in this moment, all of those ancient atoms are here, gathered together in the particular, temporary, extraordinary form that is you, resting, breathing, perhaps drifting towards sleep. It is enough to simply rest in that, to let the weight of the day fall away, and to remember that you are, in every meaningful sense, a child of the cosmos. And on that note, we will bring tonight's journey to a close. We began at the birth of the universe, in the first minutes when the only elements were hydrogen and helium drifting through the dark. We watched the first stars ignite and die, scattering the heavier elements into space. We followed those elements as they gathered into new solar systems, into oceans, into the first living cells, into the long and winding history of life on Earth. And we arrived, finally, here. The atoms inside you are ancient beyond easy comprehension, and they have traveled further and seen more than any human journey could rival. Tonight, they are resting with you. Thank you so much for joining me on the Nocturnal Astronomer. It is always a privilege to spend the quiet hours with you.